Okay, this webcast is going to talk about work and power and how to calculate both of these things. Work is one of the methods that can be used to transfer energy either into or out of a system. And working is a process that causes energy to be transferred because an external force gets applied. That means that an external agent applies a force that causes a displacement of something inside the system. So if we know the net external force and the displacement, we could calculate the work that's done as the force times the displacement. In this way of calculating it, force has to be measured in newtons. The displacement, delta x, has to be measured in meters, and it will give you work measured in joules. Work is not a vector, it's a scalar quantity, and that means it has a magnitude or an amount, but there's no direction associated with it. The standard metric unit for work is the joule, which is represented by an uppercase J. And it's sometimes helpful to understand that the dimensions of a joule are a newton multiplied by a meter, a newton meter. In order for energy to be transferred by the process of working, two things have to occur. First, an external agent, that means something from outside the system, has to apply force. And second, something inside the system has to move as a result. If there is no displacement, then no work occurred, meaning that there was no energy transfer. Let me just give an example of that. Let's say that a woman tries very hard to push a heavy box. She pushes and pushes, she huffs and she puffs, but the box does not move. It's so massive. So how much work did she do? She certainly feels tired. She was applying a force and was trying very hard. But there was no displacement. And so a physicist would say she has done zero work on the crate because it didn't move. It was sitting there on the ground at rest at the beginning, and even after she pushed and pushed on it, it's still sitting there at rest on the ground. There's no evidence that it has any more energy than it had at the beginning. So even though she did apply a force, she did not do work. There has to be both a force and a displacement for energy to be transferred. So if we have a situation like this woman who is pushing a crate, maybe across a warehouse, we are given the force and we're given the displacement of the crate, and so work is happening in this picture. The crate has moved or is moving, and so its energy has changed. This woman has done work to transfer energy to this crate. And the work is equal to the net force that she's applying times the displacement. So if we put numbers to this, let's say that she pushes a crate with an applied force of 117 newtons. How much work does she do to move it 3 meters to the right? Well, we would take the force that she's applied. She is outside our system. She's from a different system. She applies a force of 117 newtons. We multiply that by the 3 meters that the crate moved, and we could say that she has done 351 joules of work on the crate. In other words, she transferred 351 joules of energy into the system of the crate. So let's recall what we've said before about conservation of energy. An isolated system, that's a system that doesn't have any interaction with external forces. An isolated system maintains the same level of energy. There is no change in its level of energy. But if the system you're looking at has a change in its energy, then there had to have been an energy transfer. And there are only three ways for that energy transfer to occur. They're the processes of working, heating, or radiating. And so therefore, the change in energy of the system must equal the sum of the working plus heating plus radiating. Now, for our purposes, our class is only really studying the process of working. So for our problems, if there's a change in energy, it equals the work that was done on the system. And so we're going to find that we have two ways to find work. In some situations, we will be given the external force and the displacement. And so in those cases, we could calculate the work as the F times the delta X. In other situations, we may not know the external force. But in those cases, we'll be able to infer how much work was done by finding the change in the system's energy. You know, maybe the gravitational energy changed, or maybe the kinetic energy changed. The type of energy that was changed doesn't really matter. It's just that we could see how much the total energy of the system changed. That change in the total energy is the amount of work. Okay, and let's move on to power. Power refers to how fast work is done. It's the rate of doing work. And so to calculate power, we take the amount of work that was done and divide it by the amount of time that it took to do that work. So in this equation, time is going to be measured in seconds, work is measured in joules, and power is measured in watts. Watts is a new unit for us. It's represented by a capital W. So, for example, if you talk about someone who climbs up the stairs, just walking at a leisurely pace, versus someone who runs up the same stairs very quickly, they're doing the same amount of work, which was to cause a change in the gravitational energy, but one person did it more quickly than the other. It took more power for the worker to run up those stairs than it did for someone to just walk up very slowly, because they accomplished the same work, but in a much shorter amount of time. The standard metric unit of power is the watt, which is represented by an uppercase W, and 1 watt equals 1 joule per second. It's very common, like on our electric bills and things like that, to see references to kilowatts. And remember that prefix kilo, K, just means multiply by 1,000. So a kilowatt is 1,000 watts. Let's look at just a couple of examples of calculating power. So here's a tugboat that's pushing a very heavy cargo ship. The tugboat applies a force of 3.5 times 10 to the 8th newtons, and they apply that force as they make the cargo ship move 500 meters. They do that work in 20 minutes. Okay, so in this situation, we're given the force and we're given the displacement. So we can calculate the work that was done as F delta X. The 3.5 10 to the 8th newtons times 500 meters. That's how many joules of work was done. And now, if we just divide by the time, we can have the power, because power is work divided by time. One wrinkle here is they gave us the time in minutes, but for our equation to work, the standard unit of time is seconds. So we have to convert that 20 minutes to seconds by multiplying 20 times 60. And let's look at one more example of power. We have an elevator that's being pulled up at a constant velocity, and it takes 3 seconds to move from the second floor to the third floor, which is a vertical distance of 4.5 meters. Now, what kind of work is being done here? We are not given the force that's being applied by the motor, and so we're going to have to figure out how much work was done by looking at the change in the energy of the elevator. And so what's changing here is the height. It moved up 4.5 meters higher. Therefore, the work is equal to the change in the gravitational potential energy, which is the mass of the elevator times g, 9.8, times how much its height changed, which is 4.5 meters. And then once we have found the work, which is 22,711 joules, we take that work and divide by the time, which was 3 seconds, to figure out the watts of power that the motor was providing as it moved the elevator.